pi bonds
Yeah,
around
they're-
through the carbon, so there's forms resonance, but do you do it with both pi bonds, or do you just do it with one of them?
You can either do it with both. So we're gonna do resonance structures of an uncharged molecule. First thing we're gonna do is number the pi carbons. 1, 2, 3, 4. You can move pi electrons around, right? You can either move one arrow at a time, or you can move two. So if I moved one, I take the 2 electrons in this pi bond and carbon between carbon 1 and 2, and I had both electrons go to carbon 1. So that means carbon 2 now has a plus charge, right? Because it lost a bond. 1, 2, 3, 4. Still drawing in our bonds. And now carbon 1 got both the electrons from the pi bond, so there's a negative charge there.
But then the rest is the same.
The rest is the same. Now another resonance structure I could draw would be to move the pi bond between 3 and 4 towards that empty p orbital. And now I'm going to form what kind of bond between 3 and 4? A pi bond. But now if I number my carbons, just keep track of where everything went. So I still need to have a plus and a minus charge. Where's the plus charge at? Which carbon has a plus charge now? 4 does, right? And where's our minus charge at? Still at carbon 1 with the lone pairs. Alright, so we always got to make sure we balance our charge. If we start off with a molecule that has no charge, all its resonance structures better cancel out their charges. Right? Overall net no charge, overall net no charge. 3 good examples would be, oops. Okay, so you have 3 molecules here. The rules for aromaticity, the first rule is it has to be cyclic, planar, and an uninterrupted pi system. So if I label these A, B, and C, which of these are cyclic, have an uninterrupted pi system, or are planar? Cyclic in a ring. Everybody see how A and C are cyclic and have an uninterrupted pi system? Why isn't B? B has an sp3 hybridized carbon.
And that's an interrupter.
That's an interrupter. There's no pi bond. There's no p orbital there, right? To have a pi system, everybody has to have a p orbital. All right, so that's the first rule. The second rule is how many pairs of electrons does this uninterrupted pi system have? So for A, how many pairs of electrons does it have? A pi system of electrons does it have? 1. So if you have an odd number of pi electrons, what does that make you? That makes you aromatic. Okay, so that's really stable. What about C? How many pi electrons does it have, pairs? 2. So it's going to be anti-aromatic. And what about B? What is B then? B is just neither or non-aromatic.
You just got
Go for
started.
it, dude.
There it is. That'll be great in the video.
Okay, Mike.
Pump Up by Lucy. Okay, so we have a retrosynthetic problem. So we're starting with acetylene, right? This just basic alkyne, and we are forming a dichloral product in the end. So first thing you look at, there obviously we've added some what? What kind of bonds do we make here? This is globally looking at it. What bonds do we make between what elements? We turn an alkyne to an alkane, right? What else do we do? What other kind of bonds do we make?
Benzene.
Looks like we added some sort of benzene ring, so we must form a carbon-carbon bond, right? We start out with 2 carbons is all. Right? There's only 2 carbons here, and here there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. We've added 8 carbons. We've added some chlorines, right? And then we've turned an alkyne into an alkane. So we need to form some carbon bonds, we need to form some carbon chlorine and carbon hydrogen bonds, looks like. So if we take one step back and look at this. So we have an alkane. What could have been the star material for this product? What will the star material have been?
An alkene.
And an alkene. Everybody see that? Right? Could have been an alkene. So I'm just going to draw an alkene. All right, good enough. Now, what else would be on this alkene? And does the geometry matter? What else is on this alkene? What else do you guys want to put on this alkene? So why is it an alkene? So it's an alkene because, right, if you have 2 chlorines, if you put 2 chlorines on a molecule, what would the star material be to just put 2 chlorines on? Alkene. Alkenes can react with Cl2 and form a dichloral compound, right? Or we can even think about, here's 2 hydrogens that went on there. Right? How do you get hydrogens to be trans to each other? What would that have been?
So then there's a cis.
And there's the cis addition.
Is lithium or sodium?
Lithium, sodium with, right? Good. So let's take one step back. All right, so let's say this first step we're putting the 2 chlorines on. Now we're going to put the 2 chlorines on. So where would I put, so I'm just going to draw bonds in here. So if I say this is carbon 1 and this is 2, and here was 1 and here was 2, star materials here is 1 and 2. What else is on carbon 1? What should I put on carbon 1 in this position right here? If you look up at the molecule up here, what should I put at this position right here on carbon 1? Chlorine, chlorine we're adding in the steps, we want to put a hydrogen here.
Why are we adding chlorine instead of adding the hydrogen?
Can you add, you could have added the hydrogens.
It's easier to add them last though.
It's easier to add the chlorines last in this case. You could have switched those steps around if you wanted to.
So they can both add to an alkyne or an alkene?
Right. Actually, no, in this case, you can't. You have to add the chlorines last. Because those hydrogens are trans, aren't they? Do you know a way to add hydrogens trans to an alkene? They always add cis. So you have to add the chlorines last. Right. So what else is on carbon 1? What else is on carbon 1? This whole thing, right?
Yeah.
So let's draw that. You can draw it like that now because we can draw aromatic rings that way. What's on carbon 2? What's going to be cis to the hydrogen on carbon 2? Everybody see that? The methyl. Right? If you look up here, the hydrogen's going back, and so is the methyl. So on the alkene, they would also be going on the same side. And then finally, we have an H here. Good. Good so far? So if we take one step back, we have a trans-alkene. How do we make a trans-alkene? What is that? What's the star material for a trans-alkene look like? Alkane?
Alkyne.
If we have a trans-alkene, right, so we have a trans-alkene, hydrogens are trans to each other, what's the star material for that? Alkyne, right? So make it simple on yourselves, right? When I ask you what the star material is, it's going to be one of 2 things. You guys have only learned reactions for two types of functional groups. What are they? Alkenes and alkynes, right? So usually the first step back is always going to be to an alkene, and then the next one's probably going to be to an alkyne, right? So in this case, it's an alkyne. And what do we add in this step? We added the hydrogens. So the benzene ring is still here. and so is this methyl, right? So now if we go back one more step, right? What bonds do we need to add here now? Right, now we need to make our carbon-carbon bonds, right? We're going to do it separate, 2 separate steps, all right? Because we're not adding the same thing on each side. So it doesn't matter which side we choose first. It actually doesn't matter, so we could either do either side. So let's just do, oops. We'll go back one more step. And that would be all the way to this guy. Right?
So when you're doing retrosynthetic arrows, do not.
Okay, so now let's try, look at it, what do we have to do in the forward sense? So if I have this alkyne starting material, acetylene, if I want to add carbon-carbon bonds, what do I need to do? What reagents do I need to use? Na, NH2. How many equivalents do I need here? Just one equivalent, right? Because I'm just going to deprotonate one of these and form a carbanion. And which carbon, how many carbons am I going to add in this first step? So now I've made my negatively charged carbon, just the methyl, so I need a CH3 Br, right? And that adds 1 carbon. Actually, no, that's wrong.
I was gonna say, benzene.
That's wrong. So what do I need to add? I need to add the benzene ring plus a carbon that's attached to a bromine. Ready to see that? How the carbons map out? So that gets me to this. Now to get to this product, I need to add a methyl, right? So what reagents do I use first? NaNH2, again. Step 2, I need to use MEBr, right? Methyl bromide.
Can you do both those steps at the same time?
No, you really should do it 2 steps. I mean, experimentally, could you? Possibly, but as far as writing it, you need to do it 2. Okay? So now you have an alkyne, and you need to make it a trans-alkene. What reagents do you use to use that? What reagents to get an alkyne into a trans-alkene? What? From the alkyne to the trans-alkene. What reagents? The sodium solid in the NH3. Sodium solid, or lithium, NH3. That's our solvent. And then finally, what's our last step we need to add in? Cl2. So let's go through the mechanism for a terminal alkyne plus NaNH2 followed by, let's say, ethyl bromide. So the first step, we have to identify our electrophile and our nucleophile. So what's my nucleophile in our first step? So if it's, remember it's Na plus NH2 minus. What's my nucleophile? NH2 is. So those electrons will take the hydrogen off the alkyne. And these 2 electrons will go here. So normally CH bonds aren't very reactive, right? Why is this CH bond acidic? Why is this CH bond acidic? What is the key point here? Why this is acidic?
Stable product.
It's a stable product. Why is it a stable product?
Negative charge is held closer to the nucleus, and then sp, hybridized carbon.
Right. Does hybridization affect acidity? Yes. The molecular orbital this negative charge is in is an sp orbital. Sp orbitals are closer to the nucleus. The nucleus has a positive charge. It's going to make a more stable product. It's still reactive, but it's a more stable product. right? So remember that sp hybridized matters. It's a good question to ask. So now we have the negative charge, and now we add in our bromoethane. So now what's my nucleophile? What's my electrophile? What's my nucleophile going to be?
Carbon.
The negative charge on the carbon, and where should it attack?
Carbon closest to the R.
The carbon attached to the Br, right? All right, so there you go.
Whatever.
So now we just formed a carbon-carbon bond, right? So we added 2 carbons plus Br minus. All right, so that's the only way you guys know how to make carbon-carbon bonds.
How did you get 15?
All right, so how many carbons did we add? We added 1 and 2, 1 and 2. The 2 carbons we added. So now let's look at, what if I had an alkyne and I wanted to get a trans alkene? I would use Na and NH3, right? And this is at minus 78. So the NH3 is actually, right, a liquid. So it's liquid ammonia.
Did you add a carbon on that one?
Which one? Let me number the carbons. 1, 2, 3, 4, 5. Here there are 1, 2, 3, 4, and 5. Right, so I have no carbon-carbon bonds here. All I'm doing is forming a transalkene for this one. So now we have our starting material. The first step, since we're using sodium metal, sodium has 1 valence electron, right? So what's going to happen here is the sodium is going to donate an electron to the alkyne, right? Because sodium wants to have a full octet, right? So it's willing to give up 1 electron really easily. So there's 2 electrons in a pi bond. 1 electron is going to go to carbon 3. The other one's going to go to carbon 4. So electrons in the pi bond are going to split up. And the sodium is going to say it could choose 1 or 3 or 4, but it's going to go to carbon 4. Sodium's going to give an extra electron to carbon 4. Doesn't matter which carbon it went to first, 3 or 4. But sodium wants to give an extra electron to either 3 or 4. You just got to choose which one.
So what's happening with those first 2 arrows you drew?
So the first 2 arrows I drew, the pi bond has 2 electrons. One of the electron goes to carbon 3, the other electron goes to carbon 4, and then sodium comes in and gives another electron to carbon
So
4.
they're half arrows.
They're half arrows. They're fishhook arrows. That's right. So, because of what we know about electrons, do electrons want to be next to each other? No. So, we'll draw this trans. Let's look. Here's 2 electrons here and a negative charge, right? One came from the sodium. Do you think these electrons want to be next to these electrons? So would they rather be cis or trans? They'd rather be trans. All right. So now here in comes into play our NH3. So remember how we talked about a carbon that's sp hybridized having a really stable, or being able to stabilize a negative charge? What's the hybridization state of this carbon 4? What hybridization state is carbon 4? sp2. Where are these lone pairs at? What molecular orbital are they in? Is that better or worse than sp for stabilizing a negative charge? Which one's closer to the nucleus, sp or sp2? So this is going to be really reactive, right? Because these electrons are in an sp2 hybridized orbital, it's going to be very reactive. So what it's going to do is going to take an H from the NH3 solvent. Good. Okay. Now, we have to have at least, we should go back up here and say, how much sodium, we need at least 2 equivalences of sodium. All right, so we've used one, and now we're going to need another equivalent. So now another Na dot comes in, and again, is sodium willing to give up an electron? Absolutely. So it gives an electron to carbon 3. All right, the fish hook arrows, one arrow. So now carbon 3 has 2 electrons and has a negative charge. And NH3 was our solvent. So is there a lot of solvent around? Yep, so again, we said 1, 2, 3, 4, and 5. So again, our negatively charged carbon is in an sp2 orbital, so it's very reactive. And so what it's going to do is take another H, and that gets us to our product, the trans alkene.